Hi, everyone. Welcome to one of the last sessions of this conference. So I'm happy to, this session is sponsored by IQM. So I'm happy to introduce the first speaker, Yuan Su from Caltech. He's going to introduce his work on nearly tight trotterization of correlated or interacting electrons. This is a joint work with Robert Huang from Caltech and Earl Campbell from Amazon. Please go ahead, Yuan.
Thanks very much for the very nice introduction. And also I want to thank all the organizers for making this virtual conference possible. So today I would like to say something about quantum simulation, or more precisely digital quantum simulation. And the title of this talk is Nearly Tight Trotterization of Interacting Electrons. And this is joint work, which is done in collaboration with Robert Huang from Caltech and also Earl Campbell from Amazon. So the title here is slightly different from our QIP submission, but I'm really talking about the same paper. Okay, great. So the problem is as follows. You have a Hamiltonian, let's say h, and then you have some evolution time, let's say time t, and basically you just want to perform this e to the minus ith up to some accuracy epsilon, maybe quantified by the spectral norm. So as we learned from the maybe the tutorial, the problem, if we have an efficient solution of this problem, it could have applications in many different areas. For example, in physics, in chemistry, or even in designing quantum algorithms. So actually, I think later in this session, there's a talk on ground state preparation, and it's also kind of related to this digital quantum simulation. In any case, this problem of quantum simulation is actually one of the original motivations for Feynman to propose this idea of a quantum computer. So there are many systems, quantum systems, that you can consider simulating on a quantum computer. But in this talk, I would like to focus on one specific family of systems. So this is a class of interacting electrons. Here's the definition. So let's say this Hamiltonian H is decomposed into two parts. So we have this operator T and then this operator V. And then this operator T is further decomposed into linear combination of AJ dagger AK. So this is called the creation operator, and this is called annihilation operator. Well, for the V part is further decomposed into linear combination of occupation number operators. Well, hopefully you have already seen fermionic operators before, but in case you haven't, well, you can think of them as operators acting on n-qubit quantum systems. And then they are just Pauli strings, and this is called a Jordan-Wigner encoding. Okay, so you ask why we want to consider this kind of system. Well, it turns out that it can represent various systems in physics or chemistry. So for example, people are interested in electronic structure problem. Well, it turns out that the corresponding Hamiltonian can be represented as special case of this kind of interacting electrons with some chosen coefficients. So there's another interesting model called Fermi-Hubbard model, which again is a special case of this general setting. So in any case, this is a potentially good candidate problem to consider solving, simulating on a quantum computer. And this is the focus of this talk. Okay, so let's try to apply some of the simulation algorithms. Well, there are many quantum simulation algorithms that you can use for quantum simulation. Well, roughly speaking, they can be categorized into different groups according to their input model. So for example, there's a common input model, sometimes called the LCH model, maybe. So in this case, the Hamiltonian is given as a sum of terms, and each term is Hermitian and can be exponentiated on a quantum computer. There's another common model, sometimes called the LCU model, where the Hamiltonian is given as a linear combination of unitaries, and those unitaries can be efficiently controlled on a quantum computer. So basically, this controlled version of unitaries can be implemented on a quantum computer. So if you think about it for a moment, I think you can see that actually interacting electrons can be simulated in both models, right? Well, naively, you can just decompose a Hamiltonian into Pauli strings. And because Pauli operators are both Hermitian and unitary, you can efficiently implement that in both models. That's nice. We have a lot of choices that we can make for quantum simulation. But let's say, suppose we want to talk about the near-term quantum simulation, then perhaps we need to care about the resource requirements for doing this quantum simulation. So we need to understand how to improve their performance, their runtime. And there are a lot of topics that we can talk about, but here I would like to focus on one specific algorithm. I would like to have a better understanding of this Trotterization algorithm. Okay, so this Trotterization algorithm sometimes has different names. So for example, there are people calling it a product formula method, and there are also people calling it a splitting method, but they are really talking about the same thing. So, well, we already know that we can, let's say, for example, use a Jordan-Wigner encoding and decompose a Hamiltonian into Pauli strings. But actually, you can do something smarter, like more clever. So it turns out that you only have to do a two-term decomposition. So just decompose H into T plus V, because in fact, this operator T and operator V can both be efficiently exponentiated on the quantum computer. So you don't have to do that fine-grained, low-level decomposition. Okay, great. So let's use this decomposition and let's try to apply Trotterization. Well, our goal is try to approximate this ideal evolution, where we can individually exponentiate each term, and then we put them together. So this is like the first-order Trotterization. Well, we can try to use more complicated Trotterization schemes. For example, there's a family of schemes constructed by Suzuki in 1992, but of course, there are many, many other schemes that you can use. Well, I won't be focusing on a specific scheme, but instead, the results here will work for a general Trotterization algorithm. Okay, so let's talk about how to improve the performance of Trotterization, as we promised. Well, one idea I think you can use to improve the performance of Trotterization is to use the commutativity of Hamiltonian. So for example, let's say if we want to take the commutator between AL dagger AM, so this is an excitation operator, and we have this creation operator HA dagger. Well, naively, you would think you would get an arbitrary fermionic operator, but actually you are a little bit pessimistic here because in many cases you actually get zero operator. Well, the only case that you can get a non-zero operator is a case where index J is equal to index M. So there's some kind of contraction going on here. Okay, so you can get some similar situation where you take a commutator between this one and the annihilation operator. I don't want to repeat that. But in any case, how you can use the commutativity to speed up quantum simulation? Well, as far as I know, the only way that you can do this is to use Trotterization or its generalizations. So for example, let's look at this first equation. On the left, we have the error of the simulation, like the difference between the Trotterization and the ideal evolution. And then this equation tells us that basically we can just represent this error in terms of something like this. Like this looks a little bit complicated, but what is really important is a thing in the middle. So this is like a commutator. So let's say if the Hamiltonian has some nice commutativity property, then this commutator will be much smaller than the worst case, than the general case. Then you would expect a more efficient quantum simulation. Okay, so this is a first order Trotterization. You can also look at the second order Trotterization. So in this case, you have nested commutator and you get similar commutator analysis. But when you go to an arbitrary high order Trotterization, it turns out the analysis becomes more complicated and has remained elusive until very recently. Okay, so that's basically the first idea to use commutativity. The second idea that we can use is to use initial state information. So I guess there's a talk earlier this week on simulating low energy states on quantum computers. Well, actually, for interacting electrons, we can consider subspace with fixed number of electrons. So for example, we can consider this eta electron subspace. Well, in this case, the spectral norm, like our error metric, will become the so-called transition amplitude, or maximum transition amplitude. So for example, we can take the transition amplitude of this operator. It's called a particle number operator. Well, naively, if you look at this expression, you would think that this result will depend on n, because there are n objects summed up here. But actually, no, it only depends on eta, like the number of electrons, because you have some initial state information that you can use. Okay, so we can try to generalize this kind of simple observation to some quadratic fermionic operator. So for example, if you take the transition amplitude of operator T, by definition is given by this linear combination of AJ dagger AK. What you can do is you can try to diagonalize a coefficient matrix. So you get a bunch of eigenvalues, and those eigenvalues will be upper bounded by the spectral norm. Well, meanwhile, the coefficients, the indices will be contracted when you do the diagonalization. So you get a copy of this particle number operator, which will give you a factor of eta here. Okay, so we can also do another simple example where we try to bound the transition amplitude of the V part. Well, by definition, it's given by this linear combination of occupation number operators. Well, in this case, you can just upper bound the coefficients by some maximum possible value. You also have two copies of this particle number operator. Well, as a result, you get eta squared. How about the general case? Well, if you want to, let's say, analyze the performance of trotterization, you have to handle more complicated operators. So for example, you have a commutator between T and V, as we see in the analysis of trotterization. And the trick here is you can insert some projections. So let's say we have projections to the eta electron subspace. We can insert them, we break the commutator, evoke some triangle inequality, and we can just upper bound that by something like this, which is basically given by the product of these two things. Okay, great. So now we know that the performance of quantum simulation can be improved using either the commutativity of Hamiltonian or the knowledge about the initial state. But perhaps this is not the final goal that we want to achieve, because at least in the classical world, when people talk about the product developments, they are not satisfied with a product that is just a collection of features, but they really want those features to interact with each other to make something better. So here's also a quantum generalization of this philosophy. Anyway, so it's not very obvious how you can achieve this goal, because let's say if you want to use the initial state information, well, then you have to insert some projections in between those fermionic operators. Well, this will break up the commutator. You have to invoke some triangle inequality. And as a result, you are not taking advantage of the commutativity of Hamiltonian. So how is it possible that you can simultaneously combine these two types of information? Well, we prove the following results. A careful analysis of the transition amplitude of trotterization error. So let's say we are using a piece order trotterization, and we want to simulate interacting electrons. Then my claim is that the error of the simulation, as quantified by the transition amplitude, will depend on this quantity. So we see there's a factor of tau here, spectral norm of tau. We have the max norm of mu. We have a factor of eta here, the number of electrons. We also have this dependence on T. But there's no dependence on the number of qubits or number of fermionic modes. So we are really taking advantage of the initial state information. But meanwhile, let's try to compare this with the previous analysis. In the previous analysis, naively, whenever you introduce a factor of tau, you will also introduce a factor of eta. Whenever you introduce a factor of mu, you will introduce eta squared. But here, we are doing much better than that. We are trying to reduce the dependence on eta. So in this sense, basically, we are simultaneously exploiting the commutativity of Hamiltonian and the prior knowledge of its initial state. Okay, so this is the main results. And based on some of the previous experience, the analysis of trotterization could be loose for simulating some concrete physical systems. But we also have this tightness results where we construct some concrete example Hamiltonians that almost saturate the upper bounds. Unfortunately, I don't think I have enough time to go into the details of the constructions, but instead, I would like to mention some of the potential applications of these results. Hopefully, it can give you a sense of how these results could be applied in concrete scenarios. Well, one example that we have in mind is simulation of electronic structure. So in this case, let's say we have this electronic structure Hamiltonian represented in the plane wave basis. Well, we have a Hamiltonian that looks like something like this. Well, as we already mentioned, this can be seen as a special case of interacting electrons. So basically, you just define T to be this part, and then just define V to be these two parts. And you can choose some coefficients appropriately so that it's really a special case of that interacting electronic model. Okay, so we work out the complexity of this algorithm is given here. And we compare this complexity with previous complexity of previous algorithms. And what we have found is that this new result actually improves over the best previous results in second quantization, and also improves the first quantization result in some parameter regimes. So this is because we can simultaneously exploit the two types of information, whereas previous work were only able to exploit one of this information. Okay, great. So another application that we have looked into is a simulation of Fermi-Hubbard model. Well, in this case, the Hamiltonian is given as something like this. You can also try to reformulate this Hamiltonian as a special case of that general interacting electronic model. Well, it's a nearest neighbor lattice Hamiltonian. We can also get some improvement by applying these new results. This improvement is not as dramatic as the improvement in the electronic structure simulation because somehow the physically relevant regime is very close to half filling, but we are still able to improve over the best previous results in trotterization. Okay, so I think I still have a few minutes, so let me try to say something about the technical parts. If you still remember, the main goal that we want to achieve here is we want to estimate the transition amplitude of fermionic operators. Well, we have already seen how to do that for some simple quadratic fermionic operators. For example, we have this T part. We can just bound it by the spectral norm of tau times eta. When we have the V part here, we can just upper bound it by the max norm of mu and then eta squared. But what do you say about this more complicated fermionic operators? So for example, if you have fermionic operator, which is defined as something like this, where it's further recursively defined by some operator C, some operator B, you have some coefficients beta. So there's a graph illustration. So you have some coefficients interconnecting two indices. You have some contractions of indices. And sometimes you have edges connecting an index to itself. So what do you say about the transition amplitude of this fermionic operator? Well, we have some techniques that bounds the transition amplitude fermionic operator. So our first technique is based on recursion. So we start by bounding the transition amplitude of fermionic operator, and then we first bound it as the expectation of x dagger x. Well, x dagger x is a positive semi-definite, so we can further upper bound the x dagger x by contracting the indices in x and then do it in a recursive way to upper bound the original transition amplitude. Okay, so the second approach that we have here is something we call path counting. So this is more like a direct approach where we expand out x and the quantum states, and we try to give combinatorial arguments to count the number of non-zero contributions to the transition amplitude. I won't be able to present all the details of the proof arguments, but hopefully you have time to check out the paper and try to find some further applications of your. Okay, so I think I've talked for quite a while. Let me very quickly wrap up this talk. So in this work, we try to have some improved quantum simulation by simultaneously exploiting the commutativity of Hamiltonian and the prior knowledge of the initial states. Well, in the case where the interactions are sparse, like the Fermi-Hubbard model, we'll get some further improvements over the general case. We have some new techniques for bounding the transition amplitude and the expectation of general fermionic operators, which may be of independent interest. We can simulate electronic structure in the plane wave basis with a complexity that is something like this. So as far as I know, this is currently the fastest approach in second quantization. It is also faster than some of the first quantization results in some parameter regimes. We have some improved simulation of the Fermi-Hubbard model, and we construct the concrete example Hamiltonian for which the analysis is almost tight. Okay, so finally, here are some possible directions that maybe one can think about for future work. So there's a very nice talk on low energy quantum simulation earlier this week. Actually, the problem there is more challenging because the elementary exponentials do not preserve the low energy subspace. But it's very nice that people are making progress in this direction. So another property that you can use to speed up quantum simulation is to use a symmetry. So for example, there are operators that can commute with the Hamiltonian. So these operators won't damage the ideal evolution because they commute with the Hamiltonian, but they will rotate the error of quantum simulation into different directions. So when you basically sum those errors up, you can cancel those errors destructively, so you can get a faster quantum simulation. Well, there are a lot of nice work on quantum chemistry with more compact bases in this year's QIP. There are also some recent interest in designing quantum simulation algorithms for different tasks. For example, here we consider approximating evolution operator. But let's say you only care about measuring observables, then hopefully you can design more efficient quantum algorithms to do that task. We have considered the so-called quantum circuit model, where the complexity of the algorithm is determined by the number of gates used in the circuit. But of course, you can consider different cost model. For example, perhaps this kind of model is more physically relevant, is more physically motivated, and it will be very interesting to design quantum algorithms within this more physically motivated. And finally, there's a very nice tutorial given by Andrew Childs. Please go and check out this tutorial for other related work and much, much more. I guess I'll stop here. Thanks for listening.
Hey, thank you, Yuan, for the very nice talk. So if anyone has any question, they can ask in the Slack channel. So there might be a delay, so I'll start from a question. I'll start with a question that is if you use more other techniques like LCU, will it give you better results?
Yes, so well, depends on the application. So here is the comparison of different algorithms for simulating plane wave basis electronic structure. So well, we can simulate that in both first quantization and second quantization. Well, in second quantization, the result is that this new result actually improved over the best previous results. And in first quantization, we don't get a strict improvement in all parameter regimes, but we can get improvement, let's say, if I remember correctly, is when n is on the order of eta square. So in this regime, we can get a faster quantum simulation.
Okay, thanks. And from the Slack channel, Sam Pallister is asking, do you consider your results as a mutually exclusive exploitation of number conservation to the Chen et al. Paper, or could you use them both in tandem?
Can you repeat the question? Sorry.
Do you consider your results as a mutually exclusive exploitation of number conservation to the Chen et al. Paper, or could you use them both in tandem?
Oh, you mean this one? Oh,
I think
yeah,
so.
okay. So the ideas in these two papers are, I would say, completely different. So for this paper, we're using the symmetries of the Hamiltonian, and we are inserting additional extra quantum gates to speed up quantum simulation. Well, whereas here, we are not inserting any additional gates. We just run the vanilla Trotterization. And also we are not, I would say we're not using the symmetry of the Hamiltonian in a specific way. So I think that would be the difference.
Okay. Let's see if there are more questions from the Slack channel. So I also want to ask, what's the intuitive specialty of, what's intuitively what's special for the electron interacting electron model?
Well, the definition is basically given here.
Okay.
So you have a linear combination of fermionic operators.
Okay.
But you can map that into spin model by using some kind of Fermi to qubit mapping. Actually, there's a talk in parallel session on efficient construction of such mapping. But in any case, if you do the mapping, you get some familiar Pauli operators, and you can just invoke the usual quantum simulation algorithms.
Sure. Thanks. I see someone is typing.
Okay.
Yeah. Okay, so Sarah, there's 1 minute left. Maybe we could move the questions to the roundtable. We can get the next speaker prepared.
Great. Thanks
Okay.
very much.
Yeah, thank you.